We're going to go ahead and review some stuff from logs and look at using properties of logs to help us take derivatives, and then also look at logarithmic differentiation. Now, remember our general rule for our power rule is to increase your exponent by 1 and then multiply by 1 over that exponent in front, remembering you have to go plus c. And that works great except when n is -1. Because remember, 1 over x to the first does not integrate and you can't use the power rule. So we're going to go ahead and review stuff with logs. Hopefully you remember that log base c we write as natural log. Now, some of the things with logs is whatever's after your log always has to be positive. So that's what we're saying for a domain. Your range is all real numbers because it goes from -infinity all the way eventually up forever. You can draw it without ever lifting it up, so it's continuous. And then you look at your graph, you see you're always going up as you go to the right, so it's always increasing. And log graphs are concave down. Also, you should remember these properties of logarithms. Natural log of 1 is 0 because it really means e to what power is 1, which is 0. Natural log of two things multiplied together, you go log of the first one plus log of the second one. Log of two things divided, you go log of the first one minus log of the second one. If you have an exponent after a log, you can put it down in front, and it's that exponent multiplied by, or what was your exponent multiplied by your log. So, just reviewing some algebra 2 stuff, if you wanted to expand this using properties of logarithms, you have the log of two things divided, so you go log of the top minus log of the bottom. Now, when you look at this, for the second part, I'll just rewrite this natural log of an x squared plus 3 squared minus. Now, when you look at the second part, you really have two things multiplied. So you could go log of the first one plus log of the second one, which is really an x squared plus 1, and that cube root is a 1/3 power. However, you need to make sure that you're subtracting that whole thing because it's like this, so there'd be parentheses here. So basically, you just have to distribute through that negative sign, and you would get this. And now you have exponents after your logs that you could put down in front. And so you get 2 natural log of an x squared plus 3 minus natural log of x minus a 1/3 natural log of an x squared plus 1. Now, here, if you want to refresh your memory on e, we've looked at this top method before for approximating e. If you go 1 plus 1 over n, all raised to the n power, and n goes towards infinity, that's one of your definitions of e, and you get approximately this. Now, the natural log of e is the integral of 1 over, or 1 to e of 1 over t dt, which gives you 1. There's two different ways you can go ahead and look at e. We've looked at this top one before. There's an approximation of e. Remember, e is an irrational number, so it really goes on forever. It cannot be exactly represented as a decimal. Also, based on what we've done before, we've said if you have the natural log of x, your derivative is just 1 over x. Or in more general, if you have the natural log of u and you do your derivative, so you get y prime or dy over dx, it's 1 over what's after your log, and then this is the chain rule times the derivative of the inside. So derivative of a natural log is 1 over what's afterwards times the chain rule derivative of the inside. So here we're dividing variables by variables, so we can do the product rule, or I mean the quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Well, 1 over x here times x is just a 1. 1 times your natural log doesn't change it, and so we just get this as your derivative. This one here, you have this raised to the 1/2, so when you're doing your derivative, you put your exponent of 1/2 in front, decrease it by 1, and then you have to multiply by the derivative of the inside. Well, the derivative of the 1, you know, goes to 0, but the derivative of natural log of x would be 1 over x. So this 1/2 would cause a 2 to be in the bottom. This 1 over x would cause an x to be in the bottom. And then this is a negative 1/2 right here, so that would cause it to be in the bottom and in a root. And so you'd have to leave a 1 on top, basically as a placeholder to indicate that all this is in the denominator. So here you're also asked to find the derivative. However, you could do it just by going 1 over this big ugly root and then multiply it by the chain rule, the derivative of the inside, which would be really kind of ugly. Sometimes it's easier to use properties of logarithms to help us out. Remember, this is a fraction raised to the 1/2 power. So we could take that 1/2 power and put it down in front of our log. We're not doing calculus here, we're just doing algebra and rewriting stuff. We now have the log of two things divided. So remember, you can go the log of the top minus the log of the bottom. So all we've done is rewrite this using just properties of logarithms from Algebra 2. We've not done any calculus at this point. Now this, most people will find easier to take the derivative of. So you're going to leave that 1/2 in front. Then we're going to go 1 over what's after your log. Then chain rule, derivative of the inside, which is just a 2, minus 1 over what's after your log. Chain rule, derivative of the inside, which would be 4. Well, now we can just simplify this. I'm going to distribute through my 1/2, so this 1/2 would cancel out this 2, leaving me with just that first fraction, minus 1/2 times my 4 would cause me to have a 2. Well, now we just have a fraction minus a fraction, so we'd have to do a common denominator, multiply the first one by 4x plus 5 over 4x plus 5, multiply the second fraction, top and bottom, by a 2x plus 3 over a 2x plus 3. Now we can write it as one fraction over our common denominator, remembering to distribute through your -2 to your second part here. Lecture-like terms, and you just get -1 over that. Most people would find this approach a lot easier than going 1 over this big ugly root in fractions and then doing the chain rule of that. So it can be done either way, but most people find using properties of logarithms, since we're dealing with logs, an easier way to help us out. Now, this problem here does not have any logs in the problem. But sometimes if you apply a log, you can then use properties of logarithms, and it's going to make it a lot easier. Does it always make it easier? No, but sometimes it makes it a lot easier. So when you're dealing with logarithmic differentiation, you're not starting out with logs, so you just apply a natural log to both sides. So once again, no calculus. All we're doing is properties of logarithms. We can now take a look at this right-hand side and say, well, we have an ugly fraction after a log. We can just use properties of logarithms to help us out. We could go log of the top minus log of the bottom. Notice our root's the square root, and then it's cubing. It's to the 3/2. We have a cube root raised to the 4th power. So when we rewrite this, we can go log of the top minus log of the bottom. Now, once again, we have exponents here after our logs. We could put those down in front. So take our 3/2 power down in front of the first one. Take our 4/3 power down in front of the second one. Now, once again, we did not do any calculus yet. All we've done is algebra. Now we're going to go ahead and do calc and do our derivative, because it's in a form that's not nearly as complicated. So when we're doing the derivative of this, remember it's 1 over what's after your log times the chain rule, derivative of the inside, which would be a y prime. Our 3/2 stays there, 1 over what's after our log, chain rule times the derivative of the inside, which would be just a 2x, minus our 4/3 1 over what's after your log, chain rule times the derivative of the inside. So here, I would probably do a little simplifying. Notice this 2 cancels out that. And we just get a 3 and an x left on top. Here, this 3 cancels out that, so we'd have a 4 and an x squared on top. Now, we're trying to find our derivative, which is just y prime. So we need to get y prime by itself. So I could just multiply both sides by y. Now notice your original problem up here was y equaling stuff with only x's. Well, our derivative we only want with x's. Now we had a y with some x's down below. So all I'm going to do is replace what I wrote as y just with what y is, this thing here. So I'll still have my fractions, replace y with my original problem, and I get this. Sometimes it's helpful to put these as a common denominator and multiply it by this, but sometimes it doesn't really do anything and maybe even makes it more complicated. So this is an acceptable answer. Now, logarithmic differentiation works good when it's really an ugly fraction like this. Or logarithmic differentiation works good when it's a variable raised to a variable, because we cannot use the power rule when we have a variable to a variable, or when your variable's in the exponent. So we could apply a natural log to both sides. Now, you'll notice on the right side you have an exponent after a log, so you could put that exponent of x plus 1 down in front of your log. Well, now we could go ahead and do our derivative. You'll notice on the right, we're multiplying variables times variables. So on the right, we'd have to do the product rule. So 1 over what's after your log, so 1 over y, multiplied by the chain rule, which would be y prime. And 1 over y times y prime, you could write like this if you wanted. Then you do derivative of the first times the second, plus the first times the derivative of the second, which would be 1 over x. So here I'd probably distribute my 1 over x into my parentheses. So 1 over x times x, 1 over x times 1. Now we're trying to find our derivative, which is y prime. So we need to get rid of dividing by y, so multiply both sides by y. You'll notice we started out only with x's, y equaling stuff only with x's, so we want our derivative, y prime, to be only with x's. So instead of writing y, I'm going to write what y is, which is x raised to the x plus 1. So once again, when you're dealing with something after your log, to find your derivative, you go 1 over what's after your log, and then you do the chain rule. So even on a problem like this, absolute values here, remember, because whatever's after your log has to be positive. So we go 1 over what's after your log, and then we have to do chain rule times the derivative of what's after your log. Well, the derivative of cosine, you know, is negative sine. Well, a negative times a positive, you know, is a negative. And then you get sine over cosine. Well, hopefully you remember from pre-calc that sine over cosine is tangent.